Hi everyone, I'm Cobb and we are from Group 22 doing the LED E4. So this is the circuit that we built this time. It is a CharliePlexer. We provide three input and we will have 6 LEDs that lights up differently. So to explain, this is the concept that we use. By providing different combination of inputs, we will control different combination of outputs, and the circuit works like this. This is the CharliePlexing circuit. Providing 3 inputs to the freedom board, it will give up 3 outputs. By setting the output to be the data direction PDDR out and PDDR 0 for in, we can control the lighting up of LEDs individually. So for example, if I want to light up number 1, D1, we will set PTC3, which is output 1, to be 1 high, and we will set PTC5, which is output 3, to be low. On the other hand, PTC4, we will create it for PDDR 0 as an input, so that this will treat as a high impedance. The current will only flow in this way, and therefore only D1 will light up, where D2 is the counter direction of current, so it will not light up. So this is the concept that we are using for the CharliePlexer, and this is the table form that we control each of the LED 1 to LED 6, and by default it should be none, which is 0, 0, 0, creating all as input. So this will be the coding that we use this time. First we declare the switches and we declare the outputs. Then we use a table methods, which is an array, to set the output following these patterns. Let's say this is the 0, this is the 1, 2, and so on. Same goes to port high, output 1, output 3, and I will explain this later on. First we initialize the CharliePlexing using this function, enabling the clock sim SCGC5 port C mask, because we are using all port C. Port C 0 to port C PTC 0 to PTC 2 we are using for input. So pull enable is enabled, and PS is also 1, which means that it will be an active low. As for the output, we do a DSE, which is high density, for PTC 3, 4, and 5. Next, we declare the PDDR port data direction switch 1, 2, and 3 as an input, while output we will control it later in other functions. This is just to set everything to be 0. So after that, we will start having a read input function to give us an LED number. Read input function is like this. First we declare the result as 0, and we check each of the switch. So by using the combination just now, and by providing the switch to be a ground, so it will let's say in this case PDDR, we say the switch 1 is 0, then the result is 1, switch 2 is 0, the result is 2, so and so on, 1 to 6. Returning the result back to our main function, passing the result as a LED number into our setLED, and this is where the magic works. So first of all, we will declare the PDDR port for port C to set all to 0. So this is just to clear everything. The second line is more important as it uses the set output LED. So set output is the array just now, and LED is the LED that provided from our read input. So for example, if the input is 3, then it will get set output 3. So this is set output 0, set output 1, set output 2, set output 3. Set output 3 is output 1 and output 2. So what is output 1 and output 2? Output 1, output 2. LED is 3. So from here you can understand that by setting output 1 and 2, we actually declaring these two pin GPIO pin as an output. Wow, because just now we already set everything to 0, the pin 3 will be an input which has the high impedance. Next, PDOR. PDOR will provide all as output, and it depends on this port high LED. So same to just now, LED is 3, so we will go to port high 3, 0, 1, 2, 3. So output 1 is the port high 3. So what does this mean? PDOR output 1. So we setting the output as high. While only output 1 is high, so output 2 will be low by default. Or it can be known from here because we set everything to 0. So with that, we control the LED 3 to be our lighting up LED, and same concept goes to others function. Thank you, and we will go and look at the actual demonstration. So this is the circuit that we built. There is 6 LED here, controlled by 3 input. We have input 1, 2, and 3 input. So right now we will light out the first LED 1. By connecting it to a ground, it will light up because this line is to ground. This is 1. The second LED is 2. So by providing 2 to the system, 2. 3 is 2 plus 1. This is the third LED. The fourth LED is this. This is the fourth LED. This is the fifth. So 4 plus 1. Fifth LED. And lastly, 4 plus 2. You get the number 6. And thank you.
Hello, my name is Ho Jin Yong. I am from Group 22. First, I would like to do Lab 4 Part 2 Assembly Code. Well, this is our assembly coding. This is our set LED function. First, we define the variable GPIOC PDOR. Then this is our function. We push the register to the stack, and then we load the defined GPIOC PDOR to R1. Then we compare R0 with 0x01. If it is equal, then it will go to result 1. Same thing, we will go to 2, 3, 4, 5, 6. And then what is R0? R0 is parameter from main, which is the value I. Okay. So from the result one, we have the GPIOC PTDR function here. So first we load the GPIOC PTDR into R3 and then we move the 0s to s to add to R3. The 0 to 8 is in hexadecimal, which calculate from here. We actually this is our output. Then we output is 101. So all the output is equal to 0010 1000. So we change to hexadecimal, which is 0s to 8. Then back to our coding. After moving 0s to 8 to R3, we will store R3 back into GPIOC PDDR. Then turn to GPIOC PDOR. Same thing, we load the GPIOC PDOR into R3 and then we move the hexadecimal, which is 0s 08 to R3 and we store back R3 into GPIOC PDOR. Then we branch to N. Same thing is go to result 2, result 3, result 4, result 5, result 6, and we end. We pull the register back, and then we BS IR and then end. So we go to delay function. For our delay function, in MK20 microcontroller, the frequency is 21 megahertz, and which is 21 megahertz, 21 megacycle per second. So 1 second is equal to 1/21 megasecond. For our repeat function, we found that subtract function is 1 cycle, compare function is another cycle, and B is 1 cycle, and E also another cycle. So total one loop is 4 cycle. So this is our calculation for 1 second delay. First, the 21 megahertz, 21 mega subtract by 4 because it don't want the 0. Then we divide by 4, which is 524,999. So this is 0 to 524,9999. Then the 524,999 is equal to 1 second delay. Then for the delay function, we log the 524,999 to R1, and then the repeat function we subtract R1 with -1. Then we compare R1 with 0, and if it is not equal, then it will repeat this end. See our this is our
I'm Kok, and I will proceed with the main.c file. So just now my friend For Jian Yong already explained the assembly code. Now I will explain how does the C file work. So in C file we have two functions that has been declared by using the word extern. This is to link between .c file and a .s file, which is the assembly file. Two of these functions is actually in the assembly file. So in our main function, first we initialize the CharliePlexing by. So this is the initialization of CharliePlexing. It will be same as the initialization back in E4 part 1. but some small change has been made. In this case, it's the same thing that we enable the clock for port C. Next, we call the outputs for the PTC3, PTC4, and PTC5. So port direction PDDR has been set, while initialize all the PDOR to be 0. So in this part of the lab, we don't have an input, not like our part 1. So how does the function work? It's actually here. We will have an infinite loop, and within that loop, we'll check through from the reading of 1 to reading of 6. So as my friend mentioned just now, we will pass the I into the setLED function, which is the extern void setLED. So by checking the condition, whether is it 1, 2, 3 or up to 6, we will set the correct LED to light up. After each lighting up, we actually set a delay of 1 second by using the algorithm just now explained by my friend. So with this, we will make sure that the LED lights up every second. So this will be the demonstration of the circuit. So right now, this will be the first LED, second LED, third, fourth, fifth, sixth, and back to 1. So you can see that each of them are actually having 1 second's delay. And that's all. Thank you.